Hello, I'm Ron Millison, Professor of Mechanical Engineering at Cal Poly in San Luis Obispo, California. And I have an experiment here that will give us the specific heat of aluminum. Specific heat is a thermodynamic property, and calorimeters are used to measure the specific heat of materials. In a simple electric calorimeter, a material sample is isolated from the surroundings. There's a heater embedded in that sample. Electrical power input into that heater is measured. The rise in temperature is measured. The mass of that sample is known. And with these data, the specific heat of that material is computed. Now, there is always an unavoidable heat loss with the surroundings. In order to minimize that heat loss, workers have provided vacuum environments or they've used guard heaters. A guard heater backs up against the operational heater, and the power input to that guard heater is adjusted such that the temperature gradient across the interface between the two heaters is zero. When this happens, there is zero heat transfer, and that interface is considered adiabatic. Now, in another experiment, I don't minimize the heat loss to the surroundings, but instead I eliminate it altogether in the analysis. With this experiment, I have two calorimeters electrically heated with identical exterior surfaces but different interiors. The surrounding insulation around both calorimeters is also identical. I adjust the electrical power input to both calorimeters such that the exterior temperatures are the same. When this happens, the heat loss to the surroundings is also the same and can be eliminated altogether in the analysis. Now, with the current design, I neither minimize the heat loss to the surroundings nor eliminate it in the analysis. Instead, I actually measure this heat loss, and I use it to find the specific heat of the material. Here's my equipment. I call it a transient cooling calorimeter. It's a hollow aluminum cylinder suspended by two thin wires. It's closed at one end, and at the other end, it's open and fitted with a threaded aluminum plug, which provides access to a watertight cavity. Two temperature measurements are made. One thermocouple is attached to the outside surface of the cylinder with a small piece of aluminum adhesive tape. A second thermocouple is located away from the cylinder, away from the hot air plume that will rise off the cylinder after we heat it and allow it to cool. This second thermocouple will give us the ambient air temperature. Now, here's how the experiment works. I take a hot air gun and I heat the cylinder. Next, I place a draft shield over the cylinder. This draft shield has openings at the bottom, allowing air to circulate in, and there are openings at the top, allowing air to circulate out. These openings allow for the circulation of air in the chamber, but prevents any drafts from interfering with the experiment. Two runs are performed, one with water in the cavity and one without any water in the cavity. The thermocouples lead off to a digital data acquisition system, and those temperatures are recorded as a function of time and provided for you in an Excel file. I also provide the mass of the aluminum and the mass of the water. You'll take these temperature data, plot them up in Excel, fit them with trend lines, and from this data you'll be able to compute the specific heat of aluminum. And you'll see how close you come to a published value. Thank you.